Transforming raw biological inputs into a highly optimized, professional-grade culinary system requires an extreme level of precision. The entire process is built on a specific mechanic. Flavor and texture are maximized by intentionally destroying the meat's physical volume. Traditional food preparation operates on the assumption that maintaining thickness and preserving volume is the optimal way to retain internal moisture. The smash method completely discards that assumption. Here, the primary metric for success is structural crust optimization, outweighing volume retention. To execute this system, two baseline variables must be established. First, the biological input requires a cold, refrigerated baseline containing exactly a 20% lipid or fat content. Second, the assembly requires an engineered, highly acidic sauce profile to provide a precise chemical contrast. Creating the perfect smash burger requires mastering a sequence of strictly governed thermodynamic and chemical reactions. The physical state begins with cold, 20% fat ground beef, divided into highly condensed, uniform spheres. The core mechanical intervention occurs by flattening the meat sphere against a medium-high heat cast iron cooking surface. This animated wireframe shows the resulting geometric shift. As the structure flattens into a cylinder, the surface area to volume ratio increases significantly. Maximizing contact with the thermal mass of the pan is critical. It allows for rapid heat conduction straight up through the bottom of the meat. This intense thermal environment activates the mandatory 20% lipid content. Under high pressure, the solid fat melts out of the tissue. It pools exactly at the contact point, effectively frying the beef in its own expelled lipids. This intense, shallow fry triggers the Maillard reaction, a rapid realignment of amino acids and producing sugars that produces complex chemical browning. There is a rigid time constraint applied to this reaction. The system must achieve maximum browning in roughly 60 seconds. If the heat is too low or the surface contact is poor, the reaction stalls. The extended time on the heat will cause the internal moisture to completely evaporate. A successful thermodynamic exchange produces a rigid, highly textured crust that locks the physical structure in place before you execute the flip. The mechanical action of the smash forces extreme chemical browning immediately, executing the reaction before structural dehydration can occur. Immediately post-flip, the crust is established and facing upward, while the raw side cooks rapidly against the pan. The next systemic variable is introduced: cold cheese placed directly on top of the seared protein. This creates a central engineering problem. The cheese requires significant heat to undergo a phase transition into a liquid melt, but ambient kitchen air severely limits heat retention. Looking at the thermal data on this graph, the constraint is obvious. The meat hits its maximum safe internal limit of 160 degrees Fahrenheit much faster than the cheese can melt in open air. Without an intervention, you must choose between an unmelted cheese layer or structurally dry, overcooked meat. The mechanical solution is placing a physical dome over the active cooking zone. This schematic visualizes the immediate thermodynamic shift. Enclosing the system captures the existing bottom-up conduction. The dome physically traps escaping steam and latent heat released by the cooking meat. It hits the ceiling and forces it back down directly over the cheese. This newly created heat transfer mechanism is convection. Convection dramatically accelerates the cheese's phase change. It melts almost instantly, synchronizing the exact moment the meat perfectly hits 160 degrees. The dome serves as a tool for localized climate control, actively manipulating thermal vectors to align two entirely mismatched cooking timelines. The analytical focus now shifts from thermal mechanics to chemical flavor profiles and biological reception. The current system is densely loaded with lipids: the 20% fat beef, the butter-toasted bun, and the melted cheese layer. This density presents a physiological problem. An excessive fat coating on the human palate causes flavor fatigue, rapidly dulling sensory reception. The engineered countermeasure designed to prevent palate fatigue is the proprietary sauce. Mechanically, the sauce separates into two parts: pure aromatics like garlic and pepper, and a functional liquid base. The active chemical agents within that functional base are vinegar and sweet pickle relish. Combined, these specific agents provide a highly concentrated dose of acetic acid. This graphic maps the exact contrast required. The heavy lipid stack is immense, but applying the acetic acid formulation pulls the system into perfect horizontal equilibrium. Biologically, the acid operates as a solvent, chemically cutting through and stripping the fat coating from the taste receptors. This continual resetting action ensures the deep, savory notes of the Maillard crust never become biologically overwhelming. The sauce functions as a required chemical solvent, maintaining equilibrium and preventing the palate from becoming saturated. The final sequential assembly stacks the components: the bottom bun, the seared patty with melted cheese, raw onions, and the acid-laced top bun. The design utilizes mechanical compression, exploiting a 20% fat baseline for rapid crust browning. It manipulates microclimates, capturing steam under a dome to force a convective transition in the cheese, and it engineers absolute chemical equilibrium through the exact introduction of acetic acid. This schematic visualizes the completed biological structure. It operates as a single, fully optimized mechanical stack. These steps operate as strict applications of physical and chemical laws. Because they rely on pure physics rather than specialized equipment, these principles function identically in a standard home kitchen as they do in a laboratory or high-end restaurant. Precision execution of thermodynamic geometry and chemical balance yields a reliable, undeniable formula for an optimal culinary system.